This is my second day of a scientific journalism residency, and I'm in MARUM facilities in the University of Bremen, Germany. And almost as soon as I arrive, I realize something is about to be announced. An important scientific discovery.
Under the sea, scientists have uncovered vast reserves of water far less salty than the surrounding Atlantic Ocean.
In September 2025, the German outlet Deutsche Welle covered the story, offering one of the first early signs of this discovery.
The international expedition is the first of its kind, using a lift boat normally reserved for oil rigs.
A few months later, in February 2026, the story began to gain local attention, as SAT1 Regional for Lower Saxony and Bremen also covered the story.
Freshwater beneath the seafloor has been suspected for decades. But until now, there has been no direct evidence. These new findings could have global significance as water is becoming increasingly scarce.
Global water use has increased sixfold over the past 100 years, according to UNESCO's World Water Development Report, and the pressure is only growing. In times of war like this, for example, the infrastructure that supplies it is often deliberately targeted, cutting off access for hundreds of people.
Could the Iran war trigger a Gulf water crisis? Since it began, water infrastructure in the region has been hit at least 3 times, first in Iran, then in Bahrain and Kuwait. For a water-scarce desert region, an escalation could be catastrophic. This map shows the
According to projections by Cornell University in 2023, global AI demand alone could account for between 4.2 and 6.6 billion cubic meters of water withdrawal by 2027, roughly equivalent to the total annual water use of a country like Spain, or about half of the United Kingdom. And yet, for millions of people, this isn't a future problem. It's already happened, so the question is no longer whether water is scarce. It's where we might still find it. Expedition 501 of the International Ocean Drilling Program. Scientists confirmed, for the first time, the existence of fresh water beneath the seafloor of New England in the United States. And more importantly, at what stage this research stands before considering it as an accessible resource. I am Juan David Escorcia. I report on the environment, the climate emergency, and the ocean, uncovering what's changing beneath the surface and what it means for all of us. Welcome to this episode.
Impact in. Arrival. Contact in. All clear. T-L-.
Since 1968, marine scientists have been drilling into the seafloor and extracting sediments through projects like the International Ocean Drilling Program. Over the years, the goal of this program has remained the same: to drill into the seafloor at different depths, extract sediments, and analyze them. As technology continues to evolve, the result of this entire operation, bringing together scientists from all over the world, building research capacity across institutions and investing millions of dollars, is something remarkable. Vast volumes of seafloor sediments, carefully stored and studied, each layer helping to write the pages of a story about how the Earth, the climate, and the oceans have changed over millions of years. And even though I came here to understand the ocean's carbon cycle, I can't ignore this: the chance to meet the scientists behind this discovery. So I decide to reach out and step inside the heart of the MARUM laboratories.
So last year there was a scientific expedition and we collected sediments from below the seafloor. And then those cores were shipped here and they have been waiting for us to be opened.
We will do the chemical analysis, the description, what kind of different sand, clays are there.
So it's geophysics, geochemistry, geobiology, hydrogeology, yeah.
The scientists working here analyze these core sediments from different scientific fields. Each scientist approaches the core sediments by applying a wide range of techniques to extract the data they need. It's like reading the pages of a book, except in this case, each page is a cylindrical segment brought up from the ocean floor.
But some of the more complex one with like sequencing the DNA and those kind of things takes time.
And then we can measure things like how fast sound travels through sediment. We can measure like how dense the sediment is.
Between February 4th and 12th, 40 scientists from 13 different nationalities are working against the clock to meet their deadline, to obtain scientific data from 718 cores collected between May and August 2025 during Expedition 501 of the International Ocean Drilling Program. This analytical work and data collection are being carried out in this laboratory, and although Expedition 501 is not specifically designed to address water demand, the data on water scarcity and its growing pressures remain the guiding light behind research like this.
My name is Rebecca Robinson, and I'm from the University of Rhode Island.
I'm Brandon Dugan, and I'm from Colorado School of Mines.
Rebecca and Brandon are also among the scientists analyzing the core sediments in MARUM's laboratories. They are the co-chiefs of Expedition 501. Brandon explains how this marine research project first began.
So this project started for me personally in about the year 2000. We explored the occurrence of fresh water beneath the ocean based on earlier discoveries where people found it for other projects. And we started thinking about how we would really understand how this freshened water gets beneath the ocean, when it got there, and we did some numerical simulations of how groundwater flows in coastal environments. We wrote a proposal to the International Ocean Drilling Program to try and drill and study the hydrogeology of a system. That first proposal was submitted in 2003, and in 2004 we received very high rankings. And then there was a long period of discussions and fundraising and additional data that were collected that helped us improve our locations of where we would drill with a higher chance of success and limit the amount of sites that we had to drill. So we originally started out with potentially having to drill 5 sites to 800 meters below seafloor, and we ended up with 3 sites to about 400 meters below seafloor, and were able to accomplish all of our objectives. That was because we continued to study the problem. In 2023, we got selected and put on the schedule for drilling. So it was basically 20 years from the inception of the idea to being scheduled. We had an open call to people all around the world for other scientists who wanted to participate, understand offshore freshened groundwater from a hydrogeological perspective, from a chemical perspective, from a biological perspective. And we assembled a great team of scientists. We were going to drill in 2024, and we couldn't get a vessel to drill. And then a bunch of teams from IODP Cubed and the National Science Foundation put their heads together and realized that we could delay the drilling by 1 year if we found another vessel. So in 2024, we were able to secure another vessel. We confirmed the science party could still participate a year later, and we ended up with a science team of 40 people, about 39 scientists, representing I think 13 or 14 different countries around the world, who are all interested in studying offshore freshened groundwater for different reasons. And then we drilled in 2025. That's where Becky came in to help run the team. That's just making sure that we're meeting the expectations of the program, collecting water samples, getting people their personal samples. And at this point, it became a lot more personnel management than science anymore. We had to make sure that we got things done. So we had to train people on new instruments, teach people how to write reports rather than scientific papers. So we display our data and then we present it scientifically. We were both offshore for many days over the summer, really managing how the science was happening and how we could adjust operations to increase science.
So I have to say that I'm curious about the work everyone is doing here. I have seen many science from around the world working in this lab in MARUM, in the University of Bremen. So Rebecca and Brandon, in that sense, what has been the biggest surprise for you or maybe for the team during your time here?
I mean, I was and am, as I read the reports and look at the data, astonished at just how fresh the freshened water is. In my mind, I thought it would be maybe a third of the salinity of the ocean, sort of a mixture of the fresh water that we know of having basically zero salinity, and salt water, which is close to 32 in this particular region. I thought it would be somewhere in between, but closer to half or a third. And so the values that we're getting are really low. They're practically safe drinking water limits. And to me, that was truly astonishing, because how do you get this water and keep it down there without having the ocean invade over thousands of years?
For me, it's related to that, but having studied this problem for a long time and starting out with computer simulations of what we thought, we had a very simplistic view of what the ground looked like beneath the ocean, where we would have a layer of material that we call an aquitard that seals water in, and then a layer that's an aquifer where water flows, and then a layer that's an aquitard that seals water, and it's like just a layer of pancakes over all the way down. And opening these cores, there's all kinds of different aquitards and all kinds of different aquifers. There's a whole range of different sediments in terms of color and how big the grains are. We see evidence of freshened water that Becky just mentioned in material that was soil at one time, so it was deposited when there wasn't an ocean there, and then it was flooded by an ocean, and really the complexity of the geology underneath surprised me, because it's even harder for me to understand how so much freshened water got out there and it stayed, because it isn't this real simple system with a big cap on top of it that holds the fresh water. It's just a complex mixture of all kinds of different sediments, but they're all full of fresh water. And to me, that's exciting, because now I have to unravel a whole bunch of other questions, and that's what I can do for the next 4 or 5 years, as I stare at these data and work with the 39 scientists that are part of the science team.
So let's say that this expedition is raising new questions about freshwater beneath the seafloor. So how should we understand the discovery, especially in the context of the climate change or water scarcity?
There is a lot of fresh water beneath the seafloor, freshened water beneath the seafloor. But I think the questions of whether it is truly a resource, whether extraction costs would be smaller than the benefits of extracting them, I think that is still an open question with many years of research needed before it can be answered.
I think I totally agree with that. I think there's lots of long-term things about how the water could be managed, who would manage it, who would own it, things like that, which are questions well beyond my scientific knowledge. But I think we can provide data for the communities that could use and think about this in the future. I think we've also proven that you can study these systems, right? It was sort of postulated that they were large. It was proposed that they were freshened, and we've documented that. So we've proven the concept that you can go out and drill and sample these and be minimally invasive to do that. We're looking at a system that used to have glaciers. And so some of our work might translate to things maybe offshore Norway or offshore Japan, or areas where we've had, well, probably not Japan, but offshore Norway, or places where there have been glaciers in the past. We can think about those systems. But if we think about places like Indonesia or Australia or New Zealand that haven't been glaciated recently, they also have offshore freshened groundwater. So I think how we relate to those systems might require additional research as well, and to sort of understand the complexity. But I think we've proven that it can be done, and sort of what you need to do it.
I think the idea of this could be a model for studying these other systems, and first asking questions about, okay, if it was in a system that was influenced by glaciers, are they similar, or what are their differences? How much similarity is there between them? But then also, how different are these systems that weren't? I mean, I feel like these seem like really basic research questions, but until you know those answers, you shouldn't even be thinking about this as a resource, because any water you pull out, we've learned this on land, that any water you pull out in one location has impacts.
This discovery represents a milestone in the race to understand the secrets of our planet. Years of rigorous scientific research still lie ahead to understand the nature of this aquifer and to determine whether its potential use for humanity can be confirmed or ruled out. This timeline brings to mind the book The End of the Ocean by Swedish author Maja Lunde, who writes in this remarkable novel about the future of our planet. Water connects everything, past, present, and future. What we do with it today will echo far beyond our time. I am Juan David Escorcia. I report on the environment, the climate emergency, and the ocean, uncovering what's changing beneath the surface and what it means for all of us. This science journalism project was developed as part of the Frontiers Fellowship, funded by the European Union.